Hey everyone, today we're going to pull back the curtain on something you use every single second of the day, from the moment you wake up, lenses. They're literally everywhere, shaping our world, but we almost never stop to think about how they actually work. So let's dive in. So let me ask you a quick question. What do your own eyes, the camera in your phone, and a massive telescope have in common? I mean, one's biological, one captures memories, and the other peers into deep space. They seem totally different, right? So what's the connection? And the answer is lenses. That's the secret ingredient. These amazing, precisely shaped pieces of glass or plastic are like the unsung heroes of our world. They grab light, bend it, and basically build the reality that we see, capture, and explore.
Okay, so how does this bending of light thing actually happen? Well, it's not really magic, it's just some super cool physics. And it all comes down to one single fundamental principle called refraction. This is the secret behind every lens ever made.
Here's the best way to think about it. Imagine you're driving a car really fast on a smooth road, and you suddenly hit a big patch of mud. What happens? The car slows down and veers off in a new direction, right? Well, that is exactly what happens to a beam of light when it goes from the air into a piece of glass. That slowdown and that turn, that's refraction. It's the key to everything we're about to talk about. So a lens isn't just any old chunk of glass. Oh no. It's a piece that has been engineered with incredible precision, curved in just the right way to take that principle of refraction and use it to control light in very specific and, as you'll see, very powerful ways. And that really brings us to the two main characters in our story, the two fundamental types of lenses. You can think of these two simple shapes as the basic building blocks for pretty much every optical device you can imagine, from a simple magnifying glass all the way up to the Hubble telescope. So on the left, we've got the convex lens. I like to call it the gatherer. You can see how it's thicker in the middle, kind of bulging out. That shape makes all the light rays bend inward and meet at a single point. It gathers them up. Now, on the right, you've got its polar opposite, the concave lens, or the spreader. It's thinner in the middle, caved inward, and it does the exact opposite. It makes light rays spread out, or diverge. All right, let's zoom in on our first type, the convex lens. This one simple ability to focus light and bring it all to one point is behind some of the most important inventions in all of human history. Let's look at how it works. So the first and probably most amazing example is the one that's literally built right into your own head. And you've probably got another one in your pocket. Yep, both your eye and a camera depend on a convex lens to take in the world and form a sharp, focused image. When you look at something far away, the convex lens in your eye creates an image on your retina. Now that image is real, which just means it could be projected onto a screen. But here is the absolutely wild part. That image is also inverted. It's completely upside down, and it's smaller than the actual object. Don't worry, your brain is just incredibly good at flipping the image right side up for you in an instant. But what happens if we change things up a bit? What if we move the object closer to that very same convex lens? Well, you get a completely different result, one that powers every movie theater and lecture hall out there. So if you place an object, like a piece of film, at just the right distance, a little past the focal point, the image is still real, and it's still inverted, but now it's magnified. It's bigger than the original. And that's the whole secret of a projector. It's also why you have to load the film in upside down, so the giant image on the screen looks right side up to us. Okay, this amazing convex lens has one more trick up its sleeve. What do you think happens if we move the object really, really close? When the object gets super close, inside the focal length, the physics just flips on its head. The image is no longer real, it becomes virtual, which means you can't project it on a wall anymore. You can only see it by looking through the lens. And now, that virtual image is both upright and magnified. And just like that, you've created a classic magnifying glass. So we've seen how convex lenses are the masters of gathering light to focus and magnify. But what about their counterpart? Let's switch gears and talk about the concave lens. Instead of focusing, its whole job is to spread light out, to give us a much wider, bigger picture of what's going on. And the absolute perfect example of this is a little device you've probably used 1,000 times without even thinking about the cool physics behind it, the security peephole in a door. You see, unlike the convex lens with its different personalities, the concave lens is beautifully simple. No matter what, it always creates an image that is upright, smaller, and virtual. And that combination is exactly what you want for a peephole.
It takes a huge field of view from outside your door and shrinks it down into a tiny, easy-to-see image, so you can see everything at a glance. It's a lens that's designed for safety and awareness. Okay, so we get what these lenses do, but how do we measure how much they do it? How can we actually put a number on the light-bending strength of a lens? Well, that measurement is called lens power. And the logic is actually really simple. The more a lens bends light, the more powerful it is, which also means it has a shorter focal length. And we measure this power in a special unit called dioptra. And the math to figure it out couldn't be easier. The power of a lens is simply 1 divided by its focal length. Now here is the one thing you absolutely positively have to remember. For this equation to work, the focal length must be in meters. Not centimeters, not inches, meters. So let's just walk through a quick example. Let's say we have a lens, and its focal length is 25 centimeters. Step 1, convert that to meters, which is 0.25 meters. Step 2, divide 1 by that number. So 1 divided by 0.25 is 4. And there you have it. The power of our lens is 4.0 diopters. Simple as that. When you really step back and think about it, it's kind of staggering. Every single thing you've ever seen with your own eyes, every photo you've ever taken, every distant galaxy we've ever discovered, it all comes back to this simple, predictable physics of these 2 little curved shapes. They have totally redefined our place in the universe, showing us things that are incredibly tiny and things that are unimaginably far away. And that just leaves us with one final, really exciting question to think about. As our technology for making lenses gets even better, what new amazing things are waiting out there for us to finally see?